Now I give the floor to Javier. Sorry, Javier, because we take you a lot of time of your presentation, so I apologize for that. Sorry.
It's okay. Yeah, it happens. So I had prepared a lot of material. So I will likely not cover everything that I have here, but I will distribute the notebook and the slides and everything so you can follow on your own. This is quite heavy stuff, both in terms of content, technical knowledge, but also demanding of resources of your machine. Some of these things might not run on your laptop because they require a lot of RAM, a lot of processing power. And there is one part, especially at the end, that requires a graphical processing unit, like a GPU. Not all of us have one of those. You can get one of those for free for a limited period of time when you are using Colab. Oh, I have to share my screen, yeah. But if you're using Colab, almost everything should be possible to here. Entire thing. Okay, so what I'm gonna do is, my presentation had two parts. There is one slightly more theoretical and then one hands-on, very practical. The second part requires downloading some stuff, so we don't have to just sit and wait while all the downloading happens. So the idea was that you can go to this URL. Okay, so this URL here, this is a QR code. You can scan it with your phone and then you'll see the URL. If you go to this URL here, this is like a short version that it should take you to a Colab notebook. I will leave it on for a few more seconds. And once we have all access the associated notebook, we have to go there and start a few cells. While those are executing, because it takes around 15 minutes to download everything that is needed for the session, then we will be ready to do that part. While that is downloading, I will try to explain a little bit the theoretical background of all of this. Does everyone have already the notebook open or has scanned the QR code? Do I need to make it bigger or something? Yes? No, that's good. The slideshow. It's also written in a way that is easy to remember. It's basically bit.ly and then CLS INFRA _embeddings. Okay. It's everyone there or everyone who wants to follow through there. Good. So if you go there, you should see something like this, right? And then if you scroll down a little bit, there are a section of cells under setup. Okay, those are the three main cells we have to execute. But before we do that, okay, so if you scroll down, you have to execute this one, right? This one too, and then this is the big one. This is the one that takes around 14 minutes, as you can see here. All you have to do is click on the play buttons, 4 cells, and everything should be downloaded in the next 15 minutes or so. When you click, automatically, when you click on the first cell, if you're here and then you click on the play button of the first cell, Google Colab will automatically connect to a backend, okay? That backend, by default, is a regular machine with a regular CPU and regular memory, but you can change that. If you go to runtime and click on change runtime type, this is only useful for the last part, but I wanted to explain it anyway, so you're not lost when you're at home trying this. If you click here, runtime, change runtime type, you'd see a menu that resembles something like this, okay? I have more options because I'm paying money to Google to have these options open for me, but the only thing you need to know is that by default, you will have no hardware accelerator, but Google can give you one for free for a few hours if you click on the GPU. TPU is something we're not going to cover. That's another hardware accelerator that we're not going to be covering. But then you click on the GPU, and then the only option you'll have probably is the T4. Okay, and then the runtime shape would be just a standard. You will not be able probably to select a high memory RAM runtime unless you are paying $11 a month, and then you will get all these options, right? Okay. So we set up 4 cells, 1, 2, 3, and 4. There is tons of progress bar, tons of messages, so you see that everything is going fine. This is kind of battle tested, but errors might occur. Just let me know. And then while all of this is downloading, let's go back to the theoretical background part here. Well, my name is Javier de la Rosa. I am a research scientist at the National Library of Norway AI Lab. I work at the library trying to make use of AI in the library collections. That spans different modalities. I work with books, with images, with radio broadcasting, with maps, with manuscripts, basically everything you can find in a library. I try to make services useful for our patrons using artificial intelligence and language models. So in this session, there is 2 parts. The first one is the background, the one I'm going to be explaining now. The second one is a practical case using the notebook, okay? And in the practical case, we're gonna try to make an attribution of an anonymous. It's not really anonymous. It's by Austin. It's going to be Emma's, but we're gonna pretend that it's an anonymous book, and we know it belongs to either Chesterton or Austin. And then we're going to try to make all the code necessary to try to make a decision whether all the sentences in the book are more like Austin style or Chesterton style. Now, I want to start by reading a small paragraph here out loud. So embedding spaces and computational literary studies have emerged as a fruitful convergence of computer science and literary analysis. This presentation introduces the concept of embedding spaces, which represent textual data's high-dimensional vectors capturing semantic relationships and contextual information. Specifically, word embeddings enable tasks such as sentiment analysis and authorship attribution, while sentence and document embeddings facilitate analysis at larger text units. By leveraging computational methods, researchers can delve into the complexities of literature, offering quantitative insights and novel research avenues. This interdisciplinary approach holds great promise for revolutionizing the study of literature and deepening our understanding of its intricacies. That's a paragraph that reads fine, Let's keep it in mind. I want to show you now a poem by Rebecca Marshall. She's a writer that writes in Italian. Her origins apparently are Italian, and this is just a poem she wrote, like, I am a woman and I walk down the street with your head held high and an open heart to the others and to life. I am a woman, sorry for my terrible prosody. I am a woman and I like life, like a good song that makes me dance and makes me dream. I am a woman and I am strong and I am fragile and I am beautiful like life itself. I am pretty sure that none of you know this poem, basically because the poem was generated by an AI, right? I asked OpenAI GPT 3.5 model to just straight away write a poem directly in Italian using the style of Andrea Zanzotto, which is a famous Italian poet, right? And then I asked another AI to translate it to English. Google Translate uses neural models underneath to make translation feel more natural. The name is also automatically generated by another AI. Rebecca Marshall doesn't really exist. And of course, her face is absolutely artificial as well, right? For the generation of text, we use a family of models we call decoder only, which are autoregressive models. They are trained to predict the next word. By training on billions of documents, they can learn, they get a hint of what's the next word, and they're able to generate things when you ask it. The translation models are usually encoder-decoder models. That means that there is one part in this neural network internally that is able to feed the text, makes a representation, which we will see is the embedding, and then we decode that again into text, right? And then for generating faces, a few months ago, the only real options were generative adversarial network, GANs. But now this is all very familiar to you. We have ChatGPT, we have Midjourney, we have Stable Diffusion, we have JAMA models, and whatnot, right? Artificial intelligence is no longer a niche field, but their applications are in everyday use now. Now I told you to please keep this paragraph in mind, which sounds very academic, very well written. So of course I didn't write this myself. I'm not that good at writing in English. This was generated by a GPT 3.5 turbo model, which is the model that is powering ChatGPT, which probably most of you already know, right? But how did we get this far? And more importantly, why should I care about all of these models, right? So I tend to see computational literary studies, or at least the field I work at, as a mix and intertwine of different fields. There is natural language processing, there is machine learning, there is stylometry, and then a little bit of digital humanities, right? So I like to picture myself like, okay, this is what I want to do. This is really fun to do as well. But the problem is that after that comes statistics, literature, algebra, calculus, programming languages, linguistics, tons of fields. It's impossible to master all of them at once, right? It's just simply impossible. If you take a look just at NLP, natural language processing, if you take a look at the history of the field, it basically didn't exist like 60 years ago. And then after some periods in the timeline in which the whole AI just went dormant, that's what they call the AI winters, when the funding basically stops, the promises do not deliver, and then the funding agencies say we're not going to be putting more money into this, and then there is still a few rebel researchers that keep working on that, so the field gets alive again. But now we are in one of those time periods in which everything seems to be popping up again. Everything is very interesting. Everything is all over the news, and honestly, it is exhausting to work in natural language processing these days. Every week, like literally every week, there is a new revolution in the field. Every week. I read papers every day, and every 2 days, I'm not exaggerating, every 2 days, there is a new paper that is basically destroying all the previous benchmarks. It's impossible to cope, right? And the history of natural language processing is, of course, tightly coupled with the history of machine learning itself. And machine learning, it's a subset of artificial intelligence. And then all of these models belong to deep learning. Deep learning itself is a small part of machine learning. So even though now you will see in the news, like they talk about AI, but all they're really talking about is deep learning models, right? And then there is data science, which is all of these pandas, data frame, statistic stuff that some people also like to do, which kind of overlaps a little bit all of them, because it gives you a lot of tools to deal with these models, how to measure them, how to make the most of them. And this is what I was talking about before. If you see the timeline, for example, there are a couple of periods between 1973 and 1980s in which the historians of the field, I mean, I wouldn't call this a historian, but historians in the field call AI winters, right? This is when basically research stales, and then we have to wait for another new revolution to come in, and then we pick up the pace, right? But reality is that all of this is very much intertwined. We cannot see natural language processing in itself. We cannot see digital humanities in itself. We cannot see computational literary studies in itself, because all of these disciplines basically feed on each other, and they build on top of each other to progress. Personally, as I like to see it, following my own background, I study temporal logic. That's a very pure branch of logics. And then I started studying artificial intelligence. Then I did a master's degree in AI, and then I took a different path and did a PhD in literature. My idea was to try to mix everything. So as I like to see the field is basically like machine learning and NLP are progressing because they have tons of money, tons of resources, and then stylometries and digital humanities are basically trying to catch up with all the new things that just show up. This is probably kind of controversial, but it is my personal point of view. I'm not trying to impose anything on any of you. And it all started with counting words in sentences. That's wild. We have machines now that can write poems, can write reports, can write summaries, can translate, can give you recipes, can give you advice for traveling. And it all started by counting words. Literally, it all started with that. The most basic form of this counting is a technique known as bag of words. In the bag of words technique, you have a text, and then you get the unique words in that text and just count how many times those appear. When you do that with the bit corpus, then you have a way to basically turn your text into a series of numbers. Okay, those numbers have a very specific meaning, each of them. When you go from a string of characters like a text into something that is numeric, you are building effectively what is called a vector space model. That means that now every text in your corpus can be seen as a list of numbers. And you can do operations with those lists that somehow are going to have an impact on the understanding of the corpus itself. Why I say that? I say that because you can do operations with these vectors that allow you to do tasks like classification. So the bag of words model, which is basically counting words in your text and giving the absolute frequency, the number of times they appear, allow you to do classification, right? One way of seeing this bag of words, stylometries, please forgive me, is by doing authorship attribution. When you count things, and you can say that this author, for example, tend to use this many times this function word, or tend to use these other nouns always in the way he or she writes, or uses adjectives that are not very commonly used, things like that, just by counting and making a classification model based on the vector space model. The problem with this is that when you try to represent these vector space model, you get very sparse matrices, which are by definition very big, depending on the number of words you want to take into account. The matrix will be bigger or smaller, and also is not really capturing semantics. This is just lexica, counting words in your text. You can do transformation with that. You can get the stem, you can do lemmatization, you can do whatever you want, but this is just counting. It doesn't really capture what it's trying to say, what it's trying to convey. It doesn't capture the semantics. So to overcome that limitation, in 2013, Mikolov and his team came out with word2vec. Word2vec is based on the distributional hypothesis, which formally states that words that occur in the same context tend to have similar meanings. Which is to say, a word is characterized by the company it keeps. I think that's more easy to understand, honestly, and they are basically saying the same thing, right? If you tend to use a word in the same context, is because probably they have very similar meanings. If I'm talking about a visit to the oculist, and then I'm talking about glasses, probably those two contexts are going to share similarities in the way they surround those words because they are semantically related. That's the hypothesis. So working on top of this hypothesis, they build a small, really shallow neural network. We don't need to get into what actually are neural networks. It's a little bit, we don't have time for that, unfortunately. But the idea these people have is, okay, we have text, right? The quick brown fox jump over the lazy dog, right? And then you select one word. And then you have context words to the left and context words to the right. And then you train the network to be able to predict that context. You feed it a lot of text, totally unsupervised. There is no label for those texts, so it can train on literally anything. That's why these big companies are training over the whole internet. They have dumps of all the internet, like terabytes and terabytes of data, and they train on that because it does not require to have anything labeled. It's self-supervised. That's how they call it. And by using this idea, what they effectively did was to come up with a series of features that were capturing the semantics of these words. So for example, we have a vector for the word victory in whatever way you want to represent it. It could be like one hot encoded and then a vector for the word brave. One hot encoding is basically bag of words. But instead of counting the number of times, you just say when the word appears. That's it. It's a 1 or it's a 0. That's it. That's how you encode it, right? It's still a kind of a bag of words, but it doesn't give you the total frequency. So they created a network, so it was able to compress that information and then decompress it back. And in the layers in between, they compress all that information. And they realized that that information was codifying a lot of the semantics of those words. So for example, the first, let's say, is just one single layer, which is a hidden layer. You have to think about neural networks of a couple of funnels in this case, right? There is a funnel on top like this, and then there is a funnel upside down on the table, right? What we want is the part in which the two narrow parts of two funnels join. That's how the neural network is compressing the information, right? That's how this word-to-back system works, is by you put things on the funnel and then we train the neural network to say those things back. But the funnel gets narrower and narrower as you go down. So there is information that is obviously being lost. The key here is that the funnel is trying to optimize so no information is lost because it's able to recover it back. And that middle layer is what we use to represent all of these words. For example, the first unit in the hidden layer might be this column here, this dimension. So now one single of these columns or dimensions doesn't have any meaning at all by itself. If you compare that to the bag of words, we know, like, for example, this is the frequency of the word dog, or this is the frequency of the word brave. Now, to identify all of these words, instead of counting how many times they appear in a corpus, they give you a set of dimensions that are meaningless in itself. But when you put them together, they allow you to do operations on them as if you were doing operations over the semantics of the words. And that's really important because now we have all the mathematical tools in existence to do operations over semantics directly. You have captured the semantics of a word, and then you have a vector, which is a list of numbers. And now you can do you can sum those, and then you get probably something that resembles the summation of those semantics. You can do average, you can plot them. And that is really interesting, because when you plot graphically these vectors for two words that are semantically related, the two vectors are going to show really close to each other because they are capturing the semantics. And this is what happens, for example, in word2vec. When you plot things like countries and capitals, you will see that all the countries fall in a blob of your plot, and then all the capitals clustered together in another blob of the plot, right? And more interestingly, the distance between them tends to be proportional. So there is a relationship between the distances of all the countries and capitals, because these models are able to capture all of that. But in the same way they capture all of that, they are also extremely good at capturing all the biases in your text, all of it, all of them, of any kind. For example, the most common example is the king, queen, man, woman, right? The relationship between the vectors representing king and queen is very similar to the relationship between the vectors representing man and woman. But if you do the same, for example, between man and doctor, you will get something like woman and nurse. That is already encoding bias in your text, right? And the model is just basically speeding that out to you. These relationships, as I mentioned before, are basically translated to mathematical operations. So you can get the representation of the word king, which is a vector. Let's imagine that this thing is a vector here, right? Let's say it's from 0 to 1, 0 is red, 1 is blue. And then you subtract to the vector king, you subtract the semantics of man, whatever that might mean. This is extremely abstract. So you have the word king, and then you subtract the semantics of man and add the semantics of women. You now have tools to do that mathematically. And the result is something that really, really resembles the semantics of queen. And this is extremely powerful, extremely powerful to do all sorts of things: sentiment analysis, classification, authorship attribution, any kind of classification, any kind of task that can be approximated as a classification task can use this kind of information, of course, based on text, right? But not only on text. You will see that there are now models that are able to do protein folding, that they're able to do complete conversations, that are able to do they're able to play games for you, right? Now language models are basically everywhere. So now we have sparsity checked and semantics checked. So this model is a little bit better than the bag of words model we had before. The problem is that it doesn't really work at the document level. So you have words, not sentences, not whole documents, right? And these models are not good at encoding polyphony. If you say, I'm going to go for a run, or the faucet is leaking water, I need someone to cut the run, or something like that, those are two very distinct meanings. And these models are not able to capture that. The meaning that you will get is the one that is more prevalent in the corpus, right? The other less used polysemic exceptions of the words are going to be diluted in the vector. They're not going to be so easily visible, right? To tackle the problem of the documents, there is an approach that builds on top of word2vec. And the idea is that you have a corpus of documents, and then you have another model that learns a numerical representation for the entire document. You have to train the model the same way these word2vec models are trained, and then you get numerical representation of each of the documents in a given corpus. And that is extremely important. Why? Because models out there up to 2 years ago were trained on Wikipedia. They did not extrapolate very well when you use them for literary analysis. Models out there were trained on news from newspapers. They did not extrapolate if you wanted to do a historical semantic drift analysis on a given corpus, right? So you have to be very aware of how models are trained to be able to comprehend all the bias that are encoded already on those models that might affect your own analysis, right? The good thing is that after training these doc-to-vec models that build on the idea of the WAF-to-vec, the model is able at inference time, that is an operation that is orders of magnitude faster than training, and is able to generate vectors for documents that has never seen. So far we have word-to-vec. Word-to-vec gives you vectors for all the words in a corpus. If the word is not in the corpus, it's not going to give you a vector. It's an out-of-vocabulary word. That's the term. But this new doc-to-vec thing is able to give you vectors even though it has never seen the document, because it has trained on the patterns of all those documents, and then it's able to guess what the vector of a new document that has never seen is going to be. And those are document embeddings. We have word embeddings, and now we have document embeddings. Those lists of numbers, they are the embeddings. It's nothing more than lists of numbers. The same relationship that we have for words are also easy to extrapolate to the documents. For example, embeddings are close to each other when documents are semantically similar. That's a lot to say when you're working with entire books. What's the semantic of an entire book? It's really hard to say. It might have different readings. It might have different stories. It might have even different styles. It might be like a diary on some parts. It might be like a terror book on other parts, like Frankenstein. But overall, these documents are able to find at least one of those relationships, and they give it to you in the form of mathematical operations. For example, let's say I have a bunch of books, and then I plot those embeddings, right? These domino pieces might be might represent other books in the corpus, and then I do a training of a doc-to-vec model, and then I plot the 4 Harry Potter books. If the model is good enough, if the model is in domain with the same kind of data I'm going to be working on, the 4 books of Harry Potter need to be at least close to each other. Not the books, the numerical representation of those books when you plot them, right? So searching for similarities is now reduced to searching for similar vectors. So let's say I have a new book or an image or whatever you want to embed. And then the first step is to get, well, the first step is obviously to get the book. The second one is get the numerical representation. You might have trained already a model on fiction, and then you're going to use that model to get a vector back. So you get that vector back, and then you compare that numerical representation to all the vectors in your corpus. You rank by any comparison metric. For example, let's say distance. So how similar are all the vectors? So you compare the Harry Potter vector with the first vector. Oh, that's very similar. They are like 90% similar. The second one, not so similar, 10%. Third one, not so similar. The fourth one, 80% similar. Just based on a few mathematical operations, right? But those similarities can be linked back to the actual vector. And those vectors, we know they are representing specific books. So when we get those books, we can see that actually every Harry Potter book is clustering together, because this model is somehow capturing what all of these books are about. And that was all in 2013. I'm not going to go that deeply into every year, right? The idea is to be able to put to work word to vec, and then compare that to BERT models, which is kind of the new state of the art, right? But a lot happened in the last 10 years, like really a lot of things happened in the last 10 years, right? So word2vec was not very good at capturing polysemy. It wasn't very good at creating vectors for entire documents, but that was kind of solved with word2vec. The problem is that polysemy was still an unsolved task. And that's because context matters, right? This is an example extracted from a, there is someone asking on the chat, how do we get the vectors? Yeah, don't worry, we'll see exactly how the vectors are generated a bit later. So this is a scene extracted from Sesame Street. I think that's Robin Williams. And he said, hey, Elmo, what's the embedding of the word stick? And then Elmo says, well, there are multiple possible embeddings. Why don't you use it in a sentence so I can get a little bit of context and I can give you the precise vector you're looking for? Okay, here, let's stick to improvisation in this skit. Or in that case, the embedding is this, this, and that, right? That stick has a very distinct meaning if I say I'm going to grab a stick from the ground, right? Those are very, very different uses of the word stick. The lexic is the same, but the semantics is absolutely different. So Elmo was the first model to be able to incorporate all of these contexts before giving you the embedding. You train exactly the same way with unannotated pure raw text. But based on the context, it was able to generate one embedding or the other. I'm gonna have to move quickly on the internal architecture of the neural networks. But just to mention that Elmo was the first to do that. And then there was another attempt called ULM-FIT that it was not only able to do that, but also provided models that you can keep training. So let's say if you have a model that is very biased towards the medical domain, and you have a corpus of, I don't know, Spanish Golden Age theater, drama, right? ULM-FIT provided you with the tools to be able to do a domain shift in the model. The model already learned, let's say, something about Spanish is being written, but it was for the medical domain. These guys, I think it was all dudes. This team of people made a system that was able to take in an existing model and keep training it to adapt to a different domain, right? So now we are getting almost to the current state of art of language models, right? So this is how the OpenAI transformer model basically works. It's a stack of layers, and you have a sentence here like help, Prince Mayuko, blah, blah, blah. And then just based on a next word prediction task, the model is able to correctly tell you if that is a spam or not a spam. Right? It has a stack of transformer layers. There is another layer on top. Imagine, for example, when I talk about the funnel things, imagine that you cut the funnel in two, right? And then you just look for one of the sides. Those are a bunch of numbers. They have no meaning. So you need to put all of those numbers through a grid that has only two axes. Is it span or not? And that grid is the fully connected softmax layer. It's able to gather all those internal representations and channeling every piece of information into only two buckets. That's how they use these models to do classification, for example. They are extremely complex machines, but they can, in the end, be modified to your needs to do classification, right? Now it works a little bit different. but that's kind of the basic idea. So OpenAI Transformer, the currently models built on top of the ULM fit idea, like you pre-train once and then fine tune many other times. By using this kind of grid that they put on top at the end of in the middle of the panel, they were able to do classification, natural language entailment, which is an NLP task telling you when two sentences are saying the same thing. Similarity, like sentence similarity, and then even multiple choice and even question answering. So they pair chunks of text like a paragraph, and then they have a question about the paragraph and an answer, and this model can tell you if the answer actually can be inferred from the paragraph of text and the question, all by just encoding pure raw text and making the model predict the next word, and then you start to cutting through these layers and plugging in a few grids to see exactly where things need to go. And then BERT came. BERT, it's an acronym for bidirectional encoded representation from transformers, which basically put every single idea I have told in one single model to rule them all, right? And the idea was extremely successful. It shaped the entire world of NLP and our world as well. We're now finally starting to see the actual applications of these models, right? That was like 2018, so it's taking like 5 years from research to actual use, a service that everyone can use. And it was the first one. And the ideas are all the same, but instead of just predicting the next word, what these models did was, okay, we still want to have context information. We still want to have, we still want to be able to do classification at the end. We still want to do everything already. But instead of predicting just the next word, we're going to take the ideas from word to back at the beginning. And instead of predicting the context, I'm going to do the opposite. So I'm going to have a sentence. I'm going to select one word of that sentence. I'm going to mask it out, which means I'm going to tell the model that that word, I don't know which one it is. And then, but I actually know the word it is, right? So I'm going to train a model to be able to predict the words that I'm masking out. And the model is going to make the relationship between the context and the words that I'm masking out. And by doing that, it's capable of acquiring a lot of the patterns that natural language has. And that's the basics of the functioning of the BERT models. These internally, I don't know if I have something there about the internally, these models have something called the attention matrix, or the self-attention, how they call it, because it's not a pure attention, because the model is attending to things by itself. You have the text, you know the word that you are masking out, and then the model is learning when a word has this context, and the word is in fact this one, the most important words in the context to predict this one are this one, and that one. And you do that billions and billions of times. And at the end, the model learns the relationship between all the important words by paying attention to them. Attention is a fancy word of matrix multiplication, right? But the idea is that the model is able to create these big matrices. So when you put all the words in the columns and all the words in the rows, you know exactly all the values in that matrix because it's building a self-attention matrix for you. And when you have that matrix, you can do everything else. We have seen, you can do classification, you can do whatever you want. BERT is an encoder. Let me see. BERT is an encoder-only model. OpenAI is a decoder-only model. That means BERT is not capable of giving you back text. It doesn't do that. It's the upper part of the two funnels. It's the funnel that is on top. It gets the text and gives you some numbers that encode a lot of things. It can encode sentiment. It can encode I don't know, polarity, it can encode authorship, it can encode whatever you want, it can encode it, but it cannot generate text. The coder-only models, because they are trained in a different fashion, they can produce text. But to be able to produce that text, you need to give it some prior. You need to give it some previous information. And the way you do that is in the form of a prompt. The prompt is just telling the model how to adjust the internal self-attention matrix. You that extra information, and then based on that, the model knows statistically what is the next word based on the 21st words you gave, right? When you're training on raw text, that means that you can start a sentence from a book, and if the model has seen the book when training, it's going to be pretty capable of reproducing verbatim, word by word, the text. When the model is trained on dialogue, for example, rewrite this paragraph, make it sound more academic, or write a poem as if you were an Italian poet, then the model is going to be able to follow those instructions. That's instruction tuning. P5 is a combination of those two ideas. So you have one encoder, a BERT model on one side, and then you have a decoder, an OpenAI ChatGPT model on the other side, right? And by doing that, it's able to do any sort of task as long as you're able to express it in a natural language way. You can say, translate this to German, tell me if these two sentences are similar, summarize this text, and then instead of give you a bunch of numbers, which are representing the output, is able to decode those numbers back into text, right? And of course, this is also the core idea of models like ChatGPT that can maintain conversations with you as if you were talking to a human. These models are very good at making you believe that it understands, right? But it doesn't. And with this model came the whole prompting technique. They train on a massive amount of tasks, any kind of task you can imagine. There are data sets out there for English with like 2.5 million different task types. I don't know if I can do 2.5 million task types myself, right? But these models can. They have been trained on billions and billions of samples. So virtually everything you can think of is going to be there in their training data. And if it's not there, there might be 7 other samples or 7 other tasks that are kind of similar. And the model is going to be able to do the inference and the relationship between your task and the ones that's seen to give you something that is useful for you, right? That's called the zero-shot prompting. You give the model a task that has never seen, and the model is able to give you something useful based on the kind of task that is already seen. And now this is just like pure, like 3 months ago, right? They came up with this new technique called the zero-shot chain of thought. And they discovered that if you tell the model to think step by step, the model is going to be able to give you all the different steps in their thought process and then make a conclusion based on that. That's extremely important for factuality. Before these techniques, models were giving you things that look like proper English that actually kind of sound good enough, but they may be factually wrong. If you ask one of these models to say, okay, give me the result of 5 plus 6, it might give you just complete nonsense. It might sound very appealing, but it may give you complete nonsense. But by adding new techniques like chain of thoughts or prompt engineering or p-tuning or techniques like that, these models are able to give you actual answers, right? And behind the curtains, there is a lot of work going on right now about these specific use cases, because when you ask models like BART or ChatGPT or the models Perplexity or whatever model you can think of, you don't want nonsense back. You want facts. You want factual data. You want sources. You want citations, right? So, but this model doesn't, they don't know how to do that. They haven't been trained to give you facts. They have been trained to give you text that looks like English, period. That's it. That's it. If the context in which these things are asked is similar to the context you are giving the model, they're going to give you something that looks real. A couple of weeks ago, there was someone posted something on Twitter saying that a librarian complaining that someone came asking for a book that did not exist. And then after digging and digging and digging, she discovered that this person came to her asking for a book that was spitted out by ChatGPT. So the title of the book sounded really good. There was a person listed as an author, a year even. So the librarian was like scratching her head, like thinking, oh, why don't we have this book? The book never existed in the first place, right? So we have to be really careful about what these models are actually capable to do. With that, I'm gonna leave it for the theoretical part. It's only 12 minutes for for the rest, but I think it was important that you have a sense of everything that is going on about all of this. It all started with counting words. That's something that I want you to remember, right? So are there any questions so far? Hispanic, my PhD in Hispanic studies, but digital humanities, applied, very applied. I studied the authorship of the Lazarillo de Tormes, which is an extremely famous anonymous book here, and also Calderón de la Barca's Autos Sacramentales, which are plays of high allegorical content. So they are not easy to study with purely lexica-based techniques. You need to understand the semantics and the metaphors and all of that. It was pretty fun. But it's also risky to have a hybrid training, because when you go looking for jobs, yeah, you don't really easily fit. Let's go back to this theme. Hopefully all my files are still there, because this takes forever. Oh, thanks God, it's there. This is a super detailed notebook. That's why they call it literate or literate programming, something like that, because you can intertwine a lot of text with the code, right? So even though we're going to be able just to get a quarter of the whole thing, you can easily follow. The examples are very versatile in the sense that you can plug in your own text, and then the notebook won't work, but it will be close to work with your own text, right? So what is a word vector? As I mentioned before, this is just a vector. And what is a vector? Well, a vector is nothing more than a list or an array, as Python likes to call it, of real numbers, right? So this is vector 1, vector 2, vector 3, and then you can do things like operations between those vectors. You can sum them both, and then you get the result of the sum per position, right? For example, vector 1 plus vector 2 should be 1, 2, 2, 2, 4. Oh, wait a second. That's not what is happening here, right? That is because the semantics of the operations in Python lists is different than the semantic of the operations on vectors. Even though internally we might think about this list as being just numbers, the reality is that Python is a complex programming language. And to be able to tell Python to do the operations you are asking, you need to rely on a computing library called NumPy. NumPy is just short for numerical Python. And that is because, among many other things, Python allows you to put anything in a list. For example, let's say I have a list of a couple of numbers. That's still fine. And now I want a list of one number and a string of text. That's still a valid Python list. but it's not a vector anymore because vector needs to have only numbers, right? So when you do operations like this, for example, a number like that, what you get by using the plus sign in Python is just the concatenation of the lists, right? What do you think is going to happen if I do like a multiplication by 3? You get the same list 3 times, right? So it's not always intuitive what Python lists are doing. So if you want to make sure that you're working with vectors, just use NumPy. In NumPy, you can do the operations as usual. You just need to enclose your list into a NumPy array, right? All the imports at the beginning setup of the notebook. So this is very convenient where you want to do operations on vectors, right? NumPy give you a lot of things out of the box. It can give you ways to generate random numbers between a range with a specific number of with a specific distance between each other. It can also do the dot product of vectors. It can also do the vector product, which is they're very common operations that now have a very defined, very specific semantic to it. It's not doing anything strange, right? How do we calculate word vectors? Well, there is a library called scikit-learn, that's all in the setup, that allows you to do something very similar to the bag of words. We're going to go very basic, and then we're going to go step by step, building all the way to a BERT model. So we'll start with the first technique, that was the bag of words. In scikit-learn, to be able to create a bag of words, they have a class called the count vectorizer. You have, let's imagine we have a corpora consisting of only one document. In this case, a document is just a string of text. This is a simple string of text. And then this list of documents is just a list containing one string of text, right? Oh, I need to import that as well. So we can transform the document so that each word is assigned a unique identifier. That mapping between words and identifier is called the vocabulary. That's how they call it. So for example, with that corpora that I have a vocabulary size of 8 because there are only 8 unique words. There are many ways, many ways you can do that. You can lemmatize, you can ignore punctuation, you can ignore function words, you can do lemmatization, you can get the stems, right? But by default, they just count everything that is there, except for the single word letters, which is the default in this case, and the punctuation signs, right? And then you get a vocabulary size and a mapping. So now we have a vectorizer. This is already a way to transform text into vectors, a very simple one, but a valid one. Let's see how we can transform, based on this vectorizer that I have, my original list of documents. So I invoke the vectorizer, and then what I get back is something like this. So this is the identifier of the document. There is only one single document. And this is the identifiers of the words. And here I have the counts, the number of times each of these words appear in the document, right? We can also print all the frequencies together with the words, so it's a little bit clear what is happening here. And then we see that for this very first document, the word this appears 2 times, the word is 2 times, piece 1 time, off 1 time, and so on and so on. This is already an embedding of my document in this corpora. It doesn't make any sense because I'm using the same, I'm using one single document to create an embedding system, and I embedding the same document I'm using to create the embedding model, right? So this is basically useless, but the logic is the same. If you have 1,000 documents, you can still do it exactly in the same way. And when it gets out of hand, you can tell the vectorizer to only consider the 300 most frequent words, or the 200 less frequent words, or whatever logic you might want to embed in your model, right? From that, a document term matrix is nothing more than a large table, basically describing all of these frequencies per document and words, right? So in our case, we only have one document, right? So our document term matrix, it's something like this. I have in the columns all the words. It could be the most frequent ones. So far, we have not cared for that. And then we have the document, right? And each element of the array, it's already representing the document. This list of numbers is representing the document in this very corpora. So what if we have two documents now? We have the first document we had before, and then we have a second document, which is very, very similar, but it's adding a new word here, right? This word does not appear in my first document. So let's do exactly the same thing. We create this. We have everything here, but now we see that the size, oh, sorry, this is in Spanish. This should be vocabulary size. Now the vocabulary size is 9. So we have one more word in our vocabulary, right? So if we print now the counts, what we get back is at index 0, the representation of the document 0, and an index 1, the representation of the document 1, right? But you will see, or you should see, that there should be a new word for which the document 0 doesn't have any representation, and that's the word ID 8. No. Yeah, the word ID 2, right? Word ID 2 is encoding the new word new, obviously. And because that word doesn't exist in document 0, that's the key we're missing here, right? It would be the same as to have it here and just put a 0, right? But internally, usually these things are computed in a sparse way, which is an efficient way of doing computation when information is lacking. When you have a lot of zeros, you use sparse calculations, and then things can be compressed in memory, can be compressed in disk, and can be made faster. So when things contains a lot of zeros, you use sparsity, and usually you gain a little bit of computing power back. So if we compute it and put all the numbers back, what we get is something like this, right? We notice that the one-word letters were being ignored, and that really depends on your use case. Okay, so now we have a notion of what is a bag of words, how to make one. Let's just make a real one based on real text, okay? For that, we're going to be using the LTK corpus that I think Salva introduced before, right? There is a small tool there called Gutenberg, which is able to retrieve complete books from Project Gutenberg for you. You don't have to do anything, just invoking a couple of statements in Python, and then you get things back. So these are the books that are already built in NLTK. So let's, for example, get Moby Dick, Austen's Emma, and then Alice in Wonderland by Lewis Carroll. And let's just count. Let's just count a number of words. This is an approximation because we're just splitting by spaces here. So it's not doing really anything with punctuation marks, exclamation marks, and things like that. And let's print that. Let's print a few characters of Emma. And then we see that this is the format it comes in. So volume 1, chapter 1, and then the actual, well, that's how it starts, right? Emma Woodhouse, handsome, clever, and rich. That's the very beginning of the book. So let's make a corpus based on these three texts. If you have another different kind of text, you know already how to open a plain file from your disk. So the process is the same. You read the plain text file, and then you create a list with the actual text. That's your corpus. And now let's make a bag of words out of this. We have a vocabulary size just with 3 books of almost 20,000 elements. just 3 books, 20,000 elements, right? So if we want to know, for example, the word ID for peace, you get that the word ID for peace is the 12,886. So if you want to encode a new book in this bag of words, it will have like almost 20,000 dimensions. That's a really big matrix for only three plays, right? So the compute power needed for this is not going to be minimal. Even for the smallest of the literary works, it still requires a lot of compute power. So let's see how the document term matrix looks like, right? So we have our vectorizer. This is what I was talking about before as well. We have 3 documents. Those are the rows, and then we have almost 20,000 columns, right? And this is a sparse matrix because a lot of them are zeros. So by default, is using this representation that is very efficient. We can, of course, convert that back to a proper matrix with all the rows and columns with all the zeros. But that matrix is just way too big. And even just by printing a few of them, you can see that there are going to be a lot of zeros because there are a ton of words that appear in one book that do not appear in the other. And this is just with 3 books. Imagine with like 100 of them, right? So there are 3 documents with a vocabulary size of almost 20,000, and the actual number of elements in this matrix is almost 60,000 elements in the matrix with non-zero values, right? Sorry, total, out of which more than half are zeros. That's a ton of zeros to deal with. And let's see just example of the words. So we have animate, animated, animating, animation. We could, for example, make the bag of words do lemmatization, and it will reduce the size of the vocabulary, the size of the matrices, the amount of computation, and the time I have to wait sitting, looking at my screen, doing operations, right? Let's get just some of the identifiers for a few of words. For example, the word happy, sad, angry, queer, and handkerchief. Let's also use them to see how many times they appear in the corpus, not in the book individually, but in the entire corpus. So in the first book, this word appears 8 times. This word appears, the first word appears 8 times in the first book, 125 times in the second book, and just 1 time in Moby Dick. That was happy. Yeah, that was the word happy, right? Let's try to plot them. For example, this is a plot of the number of times the word queer appears in each of these books, right? We see that for some reason, queer appears a lot in Moby Dick. It doesn't appear at all in Emma, and only a few times in Alice in Wonderland. There is a study that actually analyzed how the meaning of words change over time. And they use queer as an example, because a few decades ago, the meaning was a little bit different than the meaning we see today, right? And they saw that when they studied literature. They were using queer in a very different way. So when you plot them in a semantic space, over time, they saw that the meaning was shifting towards a different kind of cluster of words, right? And this is how you discover things. And this is just counting, right? So the next step would be, now we have document term matrix. So to be able to get the word to vec stuff, we need to recalculate that matrix into something that is called the word matrix, which instead of having documents and words, it has words and words. And now we're getting close to actually getting the vector of a word. And I think I'm going to have to stop there.
Chapter 2 of the training school. Thank you. Thank you very much. I know that this is amazing. This is a different thing from what we have been teaching in the morning. and has a real high potential for literary studies. So yeah, I encourage you to go through the notebook, because the idea is that you can make once and another time all the calculation computation that we have made here at home. Probably tomorrow, next day will be the records ready for you.